Hello, my name is Shashank Shekhar and we started the first chapter of the class 11 chemistry, that is basic concept of chemistry. So in the previous lecture, we were discussing about some Dalton atomic theory and the atomic mass. So I will start with the Dalton atomic theory. We will take a quick recap of the previous lecture. Okay. So Dalton atomic theory was proposed by John Dalton. What were the main points of that theory? First was that atoms make up the matter. Okay, atoms make up the matter and they're indivisible or indestructible. Second, atom of same element were similar, means they have the same properties, whether they're physical properties or the chemical properties, they were same for similar matter. Okay, so similar atom for similar matter. Okay, then conversely we can say that different element were composed of different type of atoms. Now moving on to compound. So compounds are formed by the combination of this atom in a fixed ratio. Okay, fixed ratio of atom. They combine together to form compound. Okay, and the last one was chemical reaction is nothing but a rearrangement of chemical reaction. Okay, chemical reaction is rearrangement of atoms. Okay, so it could explain the laws of chemical combination. Very good, it was good in that, but it has drawback as it could not explain the behavior of gas. It could not explain the gas behavior. So this was the problem with the John Dalton theory. Then we discussed about the atomic mass. So what is atomic mass? So initially hydrogen was taken at the standard, but later on 112 of a carbon 12 atom was taken as one atomic unit. Means it was taken at the standard, which was later replaced by this AMU, atomic mass unit, was later replaced by 1U. Okay, so this was the atomic mass. Then we have the molecular mass. So what is molecular mass? So we consider a compound, water. So there are 2 hydrogen and 1 oxygen. So we'll simply add the atomic mass of this 2 multiplied by the down one, this number of atoms. Okay, so 2 into 1, it is the atomic mass of hydrogen, plus 2 into 16. Sorry, it is 16 only. 16 plus 2, 18U. So this is the atomic mass of water. Similarly, we can calculate the molecular mass for any other compound. But for solid, it is not the same. Example, sodium chloride. For sodium chloride and other solids, we have formula mass, a substituent of molecular mass for solid. So why this formula mass was used? Because it is not the structure we discuss about. For solid, it is not a kind of molecule, but a 3D structure. A cube is formed. Okay, and this does not compose a compound. So this is the formula mass. The method used for calculation of both this, the molecular mass and the formula mass, are same. You will simply add their atomic masses and get the desired atomic weight or the molecular weight. Then we moved on to the average atomic mass. Okay, why do we use average atomic mass? Because in nature, the atoms which are present in nature do not have the same mass. Means all of them do not have the same mass. They vary. So we take an average of them. And what was the formula for that? So for that, we have to know the relative abundance of all of those. Okay, so suppose carbon 12, it has three type of isotopes. So you have to know the relative abundance in nature in form of percentage. So we will take a summation from I is equals to 1 to n, where n is the total number of the isotope present in nature. Then we have to multiply it by atomic mass of that isotope. Okay, multiplied by the relative abundance of that isotope, and we will sum all that so that we can get our average atomic mass. So in our day-to-day calculation of science, we use this average atomic mass rather than the actual, because you cannot do it practically it is not possible to calculate each and every atomic mass and then do it, so we take its average. So this was the thing. The last thing we discussed was the mole concept. So why do we use the mole concept? So if you take at least only 1 gram of compound, any compound you take it, then it will contain a large number of atom or molecule or the entities which it is made up of, and it is difficult to handle those numbers. It is contain large number of digits, so we need to be quick in our scientific calculations. So for that we take 1 mole, which is equals to 6.022 into 10 to the power 23 units per mole. So this is the standard thing we take because of the complexity of the number we have in the number of atoms. So we take this as the standard, similar to like if you go to the market, you can ask for something, then there will be you will ask for bananas from the shopkeeper, then you say 1 dozen. Okay, so 1 dozen is equals to 12. So similar to that, this is the mole thing we have used in the science for counting purpose. This unit can be anything. It can be an atom or a molecule or an electron, any entity, doesn't matter, it will be that much mole. So this is the thing from the previous class. So we will move to today's class. So if you want to quantify things in science, we use certain type of quantities for doing that. So first one I will discuss about the percentage composition. Okay. So whenever you want to measure a compound, that what amount of element is present in it, so you use this thing. This is called the percentage composition. So how it is calculated? Suppose a compound is present, AB, this is the name of the compound, and XY, these are the number of moles that are present of that compound particularly. So you take the mass of that compound element in that compound, divided by the total mass of the compound, that is the molar mass. Yes, I have discussed the molar mass also in the previous class. So it is that mass of compound which contains 6.022 into 10 to the power 23 number of molecules. That is the molar mass or the Avogadro number of molecules. So what you will do for calculating the mass percentage, you will simply calculate the mass of that element present in one molecule, one mole of that compound, and divide by total molar mass of that compound into 100 to get our desired result. Okay, we will see an example to get things clear. Suppose we take the example water, the most easier one. We are using this water thing everywhere because you all are aware of that, I think, that the molecular formula for water is H2O, where there are 2 hydrogen and 1 oxygen. Suppose you have to calculate the percentage of the hydrogen element. Okay, so for that you must have the knowledge about the atomic mass. What is the atomic mass of hydrogen? What is the atomic mass of oxygen? So I am taking the thing that right now that you know it, and I am mentioning it here also. Atomic mass of hydrogen. I am taking approximate, or not taking the decimal thing, means after the decimal that is 0.008. I am taking round off. The atomic mass of hydrogen is 1 U, and atomic mass of oxygen is 16 U. So first I will calculate for the percentage composition for hydrogen. So what is the formula for percentage composition of element? So it is the mass of that element present in that 1 mole of that compound. Okay, so this is the mass of 1 hydrogen atom. So there are 2 hydrogen atoms. We will multiply it by 2 divided by total molar mass. Okay, so first we have to calculate the molar mass also. So molar mass of water is equals to 2 into 1 atomic mass unit of hydrogen plus 1 into 16 atomic mass unit of oxygen. So we will get it as 18.0 U. So I will divide it by the molar mass multiplied by 100. 2 9s are 18, 9 1s are 9. Then 1 will be carried here. So if you calculate it, it will be 100 by 19%. 9%, 100 by 9%. So this is your required percentage of element hydrogen in this. Further, we can calculate it for oxygen also. So percentage of oxygen in water. So you will use the same formula. First you will calculate the mass of that oxygen present in 1 mole of water. So you know it properly. It is 16, as 1 oxygen atom is present in 1 molecule of water, divided by 18 into 100. So if you calculate it further, you will get your desired result. Okay. Now, next we will move to another example for calculating the percentage composition. This is ethanol. You will study about it in the organic. So what is ethanol? So ethanol formula is C2H5OH. So 3 type of elements are present here. The first one is carbon. Carbon atomic mass is 12U. Second one is hydrogen. Hydrogen atomic mass is 1U. And the third one is oxygen. Its atomic mass is 16U. So first we will calculate the molar mass. Molar mass of ethanol. I am writing it as C2H5OH. Okay, this is the molecular formula for it. So how many atoms of carbon are present? 2. So 2 into 12 plus 5 plus 1 6. 6 atoms of hydrogen. So 6 into 1 and 1 atom of oxygen. So it will be 16 into 1. So it is 24, 6, 16, 6 for 10, 16, 1 carry, 2 to 4. Okay, 2 to 4, 1, 5. So this is the atomic mass of ethanol, which is 56U. Okay, now we will move to the next thing. We will calculate the percentage composition. It's a 46U. You can calculate it twice. So first we will calculate for carbon the percentage of carbon element. So how many carbon atoms are there? 2. The total mass will be 12 to 24 divided by 46 into 100. We will calculate this and get a desired result or the percentage composition of carbon. Then we will calculate it for hydrogen. Okay, percentage composition of hydrogen element. 6 atoms of hydrogen were present in ethanol, and one of the mass of each of it was 1. So 6 into 1 divided by 46 into 100. This is the required percentage. Then comes oxygen. So similarly, you can do this also. Do it as a homework. It will help you at exercise. It will help you to do these things easily. Now, next concept which we will move to is the empirical formula for molecular formula. Okay. So what is empirical formula? It is the simplest whole number which is present in a compound. Just it is a kind of ratio. So suppose you consider a compound which is H2O2. It is written here H2O2. So if you take their ratio, it will be 1:1. So the empirical formula for this will be HO, where 2 and 2 are cancelled out. It is a literal thing, it is not a literal thing, but you can do it to get the ratio. So 2:2, it is 1:1. So it is just the ratio of hydrogen and oxygen. So this is called the empirical formula, and it necessarily does not represent the actual formula, because you know H2O2. For those who don't know, I will writing it here. H2O2 does not exist as HO, but it exists as H2O2. So 2 atoms of oxygen and 2 atoms of hydrogen, all of them combine together to form this hydrogen peroxide. But the empirical formula for this will be HO. Okay. Then next we will move to the molecular formula. Molecular formula, we have discussed it earlier also. So it is the actual formula and represent the actual molecule for which we are discussing. So the molecular formula for hydrogen peroxide will be H2O2. The formula will be H2O2 and its empirical formula will be HO. Okay, so this is the difference between the molecular formula and the empirical formula, and it can be measured experimentally using scientific techniques such as mass spectrometry. I have mentioned this thing earlier also. So it is used to measure the mass of the atoms or molecules with greater accuracy. So we will consider here an example to do this thing, so that suppose you are given a compound and the percentage composition of every element present in that compound is given, and you are told that you have to calculate the empirical formula and the molecular formula for that. So for that, first we will consider that we are taking the 100 gram of that element or that compound for which you are calculating, compound, for more specifically compound we can say, because element will not have any elemental composition. So further we will write this at 100 gram. So we are taking 100 gram of that compound for convenience for our calculation. Okay. So we know that this is the percentage thing and it is always out of 100. So we can say that this 100 gram of compound will contain 4.07 gram of hydrogen. Okay. And for carbon it will be 24.27 gram. So this much gram of carbon. For chlorine it will be 71.65%. So it will be 71.65 gram. And its molar mass is also given. The molar mass of compound is also given. It is 98.96 gram. Okay. So this is the amount of hydrogen. This is the amount of carbon. This is the amount of chlorine. This is the molar mass of the compound. In 100 gram of compound, this molar mass will not vary. Of course, it is a intensive property. So intensive property, I will discuss this later. You will know it about in chemical thermodynamics. So something that does not depends on mass, some quantity which does not depend on mass, you can take it as molar mass or the density. It will remain same. So we will discuss it briefly, in more detail in the later on chapters. Okay. Now convert into number of moles for each element. So how do we convert it to number of moles? I have discussed it in the last lecture also. So you simply divide that element given compound, so the mass of that given compound, by the atomic mass or the molar mass of that compound. Okay. So this is hydrogen, it is 4.07 gram. You will divide this mass by its molar mass. Okay. So it is 1 U. So you will get the number of mole. So for this instant I am taking it as A. For easy calculation, you can do it by yourself on the later on part. So number of moles of hydrogen. Number of moles of hydrogen. Okay. So it will be A mole. Similarly, for carbon it will be 24.27 by 12 U. Okay. So suppose you get at B mole. Then comes chlorine. Okay, chlorine. It is 71.65. It is atomic mass is 35.5. Suppose you get it as C mole. If you want, you can calculate this. It is easier to calculate. So it is simply 4 mole. I am taking out the round off thing. Okay. This is 2 mole. Okay. This is also 2 mole. So this comes out to be the formula for, so this is the number of moles. So now we can know the empirical formula. Okay. So divide this value obtained simply by the smallest number. So what is the smallest number in all of them? It is 2. So if you write the molar mass like this, empirical formula like this, what is the compound we will get? So 3 are there: carbon, then hydrogen, then chlorine. So carbon we get it as 4. You divide by 4 by 2, you will get it as 2. You have to simply divide it 4 by 2 because it is the smallest number. So you divide by 2 only. You again divide this hydrogen by 2, 2 by 2. Okay. and this also 2 by 2. So what I'm doing right now is that I'm writing the number of mole in front of all of this compound firstly in the subscript 422, and all these of three of them I'm taking the smallest number of all between all them and dividing it by the number here. So we get it as C2HCl. Okay, so this is the empirical formula we got. Okay, so it is the molecular formula we got. We can write it here also, C2HCl. I have done it in the earlier step. Okay, now we have to know the molecular formula. So how we will do it? Okay, so we know that the molar mass we have calculated earlier, or it is given in the question only. It is 98.96 gram. Okay, so the molar mass is given here. It is 98.96 gram. And if you calculate the molar mass using this empirical formula, you will get it as 12 into 2, 24, plus for hydrogen it is 1. Okay, for chlorine is 35.5, is 24 plus 1 plus 35.5. Okay, so 30, 20, 50, 59, 60. Okay, this is the molar mass we get to the empirical formula using C2HCl. Now we will simply divide it by this. Okay, and whatever the result you get, multiply this downward atomic number by this, you will get your molecular mass. You can do it in the home also. It is easier to do. I've just left the calculation here. Okay, so this is the thing about the empirical formula and the molecular formula and how you can calculate this. I have given an illustration here. You can practice some question given in the NCERT. It is given there. Okay, next thing we will move to, it is called stochiometry and stochiometric calculations. Okay, so you must have heard this stochiometry thing in the 9th and 10th class also. While you were balancing some chemical equation, there is some kind of stochiometric coefficient present in before each of the compound. So why this stochiometry thing is important? So it is important in two ways. First is the qualitative one, and second is the quantitative one. So how it is helping in the qualitative manner? So you can use this coefficient thing, this stochiometric thing, and know that what are the reactants and products involved in the reaction. Okay, in the compound. Okay. The second thing we will get to know is the physical state of the reactant and product using that equation. Okay, so two things we can get from a chemical equation. The first one is the reactants and product present in that reaction, and the second is what is the state. Suppose a reaction is occurring like this. There's H2O. You can take another example also. Suppose we are taking HCl. Okay, so HCl or AgCl, any other salt we can take. So HCl is not a salt, HCl, AgCl are taking, and we are dissolving it in water. Since this salt is partially soluble in water, it is sparingly soluble salt. So this salt will dissociate partially and an equilibrium will establish between both of them. Equilibrium, you can think of a state where there is no change in the reactant or product composition. So you will get it as Ag plus aqueous and Cl minus aqueous. Okay, so you can see here we can get the idea about which compounds are involved, and which elements are involved at least. This is silver, this is chlorine is there, silver chloride is there, silver ion and chloride ion. This is the spaces present here. Also, you can get the state. So AgCl or silver chloride is present as solid, and this ion, it is present in aqueous form, which is stabilized by water molecules. This chloride ion, it is also present in aqueous form, and it is also stabilized by water molecule. Next thing we get from the chemical equation is the relative amount of the reactant product. Okay, so you can see the coefficient, there is no coefficient present here, but this means that 1 is written here. Okay, so you can get the amount of reactant and product that are present during a reaction using that chemical equation. And how does we know? In terms of moles, okay, or in terms of molecules also. So if you want to convert moles into molecule, you can do and get that thing. Okay. So consider an example to illustrate the importance of a chemical equation. So we are considering the example of combustion of methane here. So what does happen when the methane is oxidized or burnt? So it combines with oxygen, undergoes combustion to give carbon dioxide and 2 moles of water. So 1 mole of methane combines with 2 moles of oxygen. They both are in gas state. We get carbon dioxide, 1 mole of carbon dioxide, which is also in the gas state, plus 2 moles of water, which is in the vapor state, are the same. You can say it as gas state. Okay. So what can we derive from the above equation? Similar thing is written here, that 1 mole of methane combines with 2 moles of oxygen to get 1 mole of carbon dioxide plus 2 mole of water. Similarly, we can say one more thing. If you want to say it in a more simple fashion, if you do not know much about mole, you can say that molecule, in terms of molecule, that 1 molecule of methane will react with 2 molecule of oxygen element compound to get 1 molecule of carbon dioxide and 2 molecules of water. Also, if you know to calculate the molar mass of each of them, then you can find the amount of that compound in terms of gram also. So if you know the atomic mass, which I know, so I will calculate the molar mass. It is 12 plus 1 into 4. It will be 16 gram. It will be 2 into 16 into 2, 32 is 64. Okay, 64 gram. Carbon, it is 12, 16 to the 32, 2 to 4. It will be 44 gram. And water we have already calculated is 18, so it will be 36 gram. So if we are taking 1 mole of each of them, so we'll get to know that 16 gram of methane will react with 64 gram of oxygen to get 44 gram of carbon dioxide and 36 gram of water. You can see clearly how important this chemical equation is and what kind of important information you can get it through this. You can get the number of moles. You can get the number of moles. I'm writing down it here. First one, we will get the number of moles. Second, we will get the number of molecules. Third, we will get the mass. And if we are considering and knowing the density of each of the gases, we can also get the volumes. Okay. So volume is nothing but mass into density. Okay. Let me see. So density is equal to mass per unit volume. So volume will be mass by density. Okay. Volume is equal to mass by density. So you can see here, this all 4 things you can get simply by getting the chemical equation: mole, molecules, mass, volume. Many more things can be derived using this. So the state also, you can see here the state is written. Now you can also get an idea about the limiting reagent using the chemical equation. So what is limiting reagent? So when we react 2 things, then the equivalent of both of them should be present according to the chemical equation, so that reaction could be completed and we get the complete reaction. Okay, but sometimes one of the reactant is not presenting appropriate amount to react properly. So how do we know that which should be taken in what amount? So you can do it by chemical equation. While if a reaction stops in a way, so we can know using that chemical equation and the knowledge of mole concept that which is the limiting reagent in that reaction. So suppose these things are written here also. So reactant present in least amount relative to the stoichiometric. It is just in language. So it is important to consider the stoichiometric calculation. Okay, this is the stoichiometric calculation of the mole calculation. So we consider here an example. So this example says that we're taking the same example for the combustion of methane here. So according to this equation, we can say that 2 mole of oxygen react with 1 mole of methane. Okay. So if you know the unitary method, you can calculate it easily. I'm telling it one more time here. So it is written that 2 mole react with 2 mole of oxygen react with 1 mole of carbon. Okay, methane, sorry, 1 mole of methane. So by unitary method, you can say that 1 mole of oxygen react with 1/2 mole of methane or CH4. But we are given 3 mole of oxygen. So you can say that 3 mole of oxygen will react with, we'll simply multiply it 3 into 1/2. It will be 2 into 2, 1.5 mole. Okay, 1.5 mole of methane. But we see here that we are given only 1 mole of methane. Since methane is present in limiting amount as compared to oxygen, which is present in more amount, its equivalent is present in more amount. You can say it more clearly that equivalence is present in more amount. So this methane thing here is the limiting reagent for this given reaction condition, that is 3 mole of oxygen and 1 mole of methane. Okay, so you can see that how helpful this chemical equation is and how we can calculate this limiting reagent thing using the stoichiometric calculation. You also need to have a little knowledge about the unitary method. It is very helpful. Okay, now next thing we will move to the concentration. Okay, so whenever we deal with a reaction in labs or in our scientific world, we need some sort of concentration thing to deal this compound more easily. Often we do not take the mass or anything because we have to deal with solution also. We have to deal with gases also. So each and every time we cannot just use the mass as for the greater thing. Okay, so many of this concentration type are used. The first one is written here, it is as mass percentage or weight percent. Okay, second one is the mole fraction, third one is the molarity, fourth one is the molality. Okay, so first we will discuss the mass percent. So what is mass percent? It is nothing but simply the mass of the solute and the mass of solution, both are divided by each other, multiplied by 100. So for those who don't know what is solute and solvent, so whenever you make a solution, suppose you are making a sugar solution, you take water, okay, and you put the sugar in it, okay, and make the solution. So the sugar which you are dissolving, this thing is called the solute, and the thing in which we are dissolving the solute, it is called the solvent. So for the mass percentage calculation, suppose we are calculating the percentage solution of percentage mass of solute. So we'll take mass of solute. Okay, this is the mass of solute. So in this case, it will be mass of sugar for this particular case. Okay, we will take mass of sugar divided by mass of water in which we are dissolving it. Okay, sorry, oops, water into 100, and whatever the amount we get, that will be the percentage solute in that solution. So here example to make things more clear. So I am preparing a solution. We are taking 2 grams of a substance and dissolving it into 18 grams of water. Let's call that substance A. Okay. So what is the mass percent of solute? Mass percent. You can say mass percent or mass percent of solute is same thing. Okay. So 2 grams divided by total mass of the solution. What is the total mass of the solution? It will be 18 plus 2. Okay. Multiplied by 100. Okay. So I have written it here wrong. You can correct it. It is mass of solution. That is mass of water plus sugar. Okay. So it will be 18 plus 2, 20. 2 by 20 into 100. 25 is 100. 5 to the 10%. So this solution, it's 10% by weight. This is a way of saying about mass percentage. Okay. So we simply don't say 10%, but instead of that, we say that 10% by weight. That's that the substance A is present by 10% by weight in water. Okay, or in the solution more particularly. The next thing we will discuss is the mole fraction. So what is mole fraction? So mole fraction is simply the number of moles. Suppose you have to calculate the mole fraction of A. So it is simply the number of moles of A divided by the total number of moles of that A present in a solution. So in our recent discussion, we have seen in the slide that we are discussing about the solution thing. So next also we will discuss about molarity and molarity. Those will be about solution only. So we are discussing mainly about solution. You should keep in mind. You should keep it in mind. Okay. So here is the thing. So if you want to calculate the mole fraction of A, so it will be number of moles of A divided by total number of moles of the solution. So Na here represents the total number of moles of A. Na plus Nb, that is moles of A plus moles of B. It is a binary solution, means two of the components are present, A and B. So we simply add their moles and keep it in the denominator, and in the numerator part we will take that's the mole fraction of which we are calculating. We will take its mole and write it here, and by dividing we will get our desired mole fraction of A. Similarly, for B, if you want to calculate, you will take the total number of moles of B divided by total number of moles in the solution, that is Nb by Na and Nb, where this symbol signifies the same in the previous thing. The significance is same. Okay. Now suppose we take an example to make things more clear. Suppose you are taking a solution, given a solution, okay, and said that number of moles of A which is present is 5. Okay, 5 moles are present. And number of moles that is present here, it is 15 moles of B. This is a binary solution. No other components are present. Only A and B are present. So if you are told that you have to calculate the total number of moles of A, so how you will do it? So Na, I am representing mole fraction by Xa. So this is the general way of representing the mole fraction. Okay. Xa is equals to Na by Na plus Nb. So this is the important thing you have to notice. It is not Xa. For if we particularly you can say chi A. Chi is just a Greek word. It is chi. Chi. Chi A is equals to Na by Na plus Nb. So what is the number of moles of A? It is 5. Okay. And total number of mole will be 15 plus 5. Na plus Nb, that is 5 plus 15. 5 by 20. So it will be 1 by 4. Similarly, for B, you can write it as Nb by Na plus Nb, where chi B is the mole fraction for B, is equals to 15 by 20. Total number of moles I calculated earlier. So 5 3 is 15, 5 by 20. This is the mole fraction of A, this is the mole fraction of B. For binary solution or any other solution, you can remember a trick, simple trick. For binary solution particularly, you can say it more appropriately. For binary solution, that suppose you have calculated the mole fraction of A using this formula, then you do not need to calculate for B. Okay, just simply subtract it by 1, because this is a fraction, so total will be 1. So if you subtract it, 1 minus 1 by 4, you will get the same result. Okay, so you can use this trick everywhere and make your calculation in science more easier rather to calculate it twice. Okay, now next thing we will move to molarity. So it is the most accepted and the most widely used concentration thing used in scientific calculation, and particularly in labs or in our daily research thing. We use this molarity thing everywhere. I will tell you the main difference between molarity and molality in later on, when we will come to know molality also. So why do we use molarity more as compared to the molality? So what is molarity? Molarity is the total number of moles of solute that is present in the solution divided by volume of the solution in liter. Okay, and this volume will be in liter always. I mean, it is a standard thing. It will be mole, so you can get the unit also. So what will be the unit for it? It will be mole per liter. Okay, so this is the derived unit from if we have calculated using the base unit. Okay, here. Then we will move to denoted by M. It is denoted by capital M. So first we have seen the mass percentage. Then we have seen the mole fraction, which was represented by chi. In the subscript, we write the appropriate element or the compound for which we are calculating the mole fraction. then this denoted by capital M. So why I'm saying it capital M, you will know it in the later on slides. Now let us take an example. Suppose you have to calculate the molarity of this solution, okay, and the data which is given here, it is that is given, it is that the mass of NaOH solution is 4 gram. Means 4 gram of NaOH is dissolved, and the volume of solution in total, that is 250 ml. So you can convert it using the unit factor. This will be your exercise to do, or I will do it here also, you can see. So milli centi decigram, you have to convert in 10 to the power 3, it is 1000. So 1 liter is equal to 10 to the power 3 milliliter, or 1 liter by 10 to the power 3 milliliter is equals to 1. So this is the unit factor, okay. Since we need to convert it into liter, so we'll keep the milliliter thing down. So 1 liter by 10 to the power 3 milliliter. This milliliter thing will get cancelled out. Not in the literal sense, always I take it as in the tricky way. So 250 into 10 to the power 3. Now you can convert it into scientific calculation. You must do these things in each and every question because it will make your and sharpen your basics more clearly. So you have to move your decimal to the left side, so by 2 digits, and since we are moving to the left side, so you have to do it in the positive way, as on the right side we increase the exponent by negative way. So 2 digits, 2.50 into 10 to the power 5, 3 plus 2 I am adding here, you know it, okay. We get it as the volume of the solution in a scientific notation way, appropriate scientific notation way, okay. For calculating the mass of NaOH, you have to first calculate the molar mass of NaOH. Mass, not moles of NaOH. So for calculating the moles of NaOH, you have to know the molar mass. So how we calculate the molar mass? I am doing it in a quick fashion, okay. So for sodium it is 23, 1 atom of sodium. For oxygen it is 16 to the 16, okay, 16 only. For hydrogen it is 1, 16 plus 1, 17, 17 plus 23, 17 plus 23, it will be 40. So it is 40, okay. So you will divide by number of molar mass to get the number of moles. So it is here, okay, gram per mole, 40 gram per mole. So 1 by 10 moles. So you have calculated the number of moles. You have the idea about the volume of the solution. So what will be the molarity? So you will simply use the formula that number of moles, that is 1 by 10. I am writing it directly. 0.5 into 10 to the power 5. You calculate this quantity. Suppose you get it as A. So this will be a final answer. Do not forget to put the symbol here. That is the unit of molarity. It is capital M. Okay. Okay, I have left the space here, but I have calculated in the first page only. So we will move to next one. Okay. So the next thing is molality. So what is molality? Okay. So molality is calculated as follows. It is the number of moles of solute divided by mass of solvent in kg. Okay, remember this thing. It is important to remember it. That is, it is number of moles of solute divided by mass of solvent in kg. So you can say it simply in more familiar way that it is the number of moles present in 1 kg of solvent, means number of moles of solute present in 1 kg of solvent, and it is denoted by small m. See, I have mentioned here in the earlier molarity that it was represented by capital M, where it is, in this case it is represented by small m. So for that I have mentioned the caps. Okay. Now we will take an example to calculate the density, using the density to calculate the molality. Okay. So what do we need for molality? First we need to know that what is the moles of solute. Okay. So the density of 3m solution, so density is given 3m. Density is given 1.25 gram per liter. Density is given at 1.25 gram. Now 3 ml solution is taken. Okay. So what do you can say about it? That in 1 liter of this solution, okay, 3 moles of NaCl is present. Okay. You can convert it into mass as we need the mass. Okay. You can convert it into mass or left it, leave it. No, you need it. Okay. So you have to calculate it in mass. So for mass thing, you have to know the molar mass of NaCl. So molar mass of NaCl, I will again calculate it in a quick way as I have calculated earlier. So you must have known the thing. So for sodium it is 23. Okay. Plus chlorine it is 35. So it is 5 plus 3, 8. 2 plus 3, 5. Okay, 58 gram per mole. So I multiply it by 3 into 58. We will get it as 174 gram. So this is the mass of sodium chloride present in 1 liter of that solution. Okay. Now, okay. So what is the mass of the solution present in 1 liter of solution? It is the mass of NaCl. NaCl present in 1 liter of solution. It is the mass of solution. Mass of 1 liter of solution. So we know the formula that density is equals to mass per unit volume. So mass will be equal to volume into density of that solution. So volume it is 1. It is written here. And it is 1.25. We will get it as 1.25 gram. Okay. So this is the thing. Okay. Now this is the mass of solution. And the mole, it is 3 moles are present here. Okay, I'm using it. We do not need it. Sorry for that. So molality is equals to 3 by 1.25 m. So this is the molality we get. So we have seen many things here. For concentration thing, we have seen molarity, mole fraction, and mass percentage. Okay. Then we have seen the percentage composition. We have seen the chemical equation and how limiting reagent can be calculated. Okay. So one thing we have left is, why do we use molarity more instead of molality? Do not get confused with the pronunciation. It is LITY and it is RITY. So the main difference with molarity and molality is that it varies with temperature. The molality thing varies with temperature, but the molality thing doesn't. So it is more appropriate to use the molarity thing. Okay. So thank you all of you for the time. This was my lecture.